Today we'll be doing a data science interview about k-means clustering. Hi everyone, we're here for another Exponent mock interview with Jimmy. For those of you who aren't already familiar with Exponent, Exponent helps you get your dream tech career with our online courses, expert coaching, peer-to-peer mock interviewing platform, and interview question database. Check it out at tryexponent.com. All right, thanks so much for being here with us today, Jimmy. Would you quickly introduce yourself for our viewers?
Yeah, nice to be here. Thanks, Angie. I'm a machine learning engineer by trade. I'm currently on a science team at Amazon, although I've worked at other companies, large and small. And before industry, in a past life, I was a student at Stanford and Berkeley, where my research was in theoretical computer science.
Awesome. All right, so let's get right into it. So today we'll be doing a data science interview about k-means clustering. All right, so I'd like to start out with discussing a little bit about what the actual objective is for k-means. So we have a notebook set up for you if you want to share your screen that has a little bit of synthetic data set up for this problem.
Okay.
Okay, perfect. So as you can see here, we have some synthetic data set up that we'll be using for this problem. It looks like roughly like there's 3 clusters maybe, but we'll find out via k-means clustering later. So my first question for you is, can you define the clustering problem and give the form of the objective?
Sure. So the clustering problem is a problem in which is an unsupervised problem, meaning that we're given a bunch of points, let's call them X, and we're not given labels. And we're also we might be given a number, an integer k, of clusters that we want. And then our job is to assign each of the points to one of these k clusters, or basically group them into k sets.
Okay, awesome. And so what kind of learning objective would you use in order to actually cluster the data points?
Sure. So a very common one is called k-means objective, which basically says cluster the points so that, or more specifically, choose k mean points or centroids, such that if you think about each point as being assigned to its nearest centroid, this choice of centroids minimizes the distances within each cluster, or the sum of the distances within each cluster.
Mm-hmm.
So see here you have a place for me to write it down. So maybe I'll write this down more precisely. So let's think of our clustering as being defined, like I said, by these k mean points or centroids. So I'll call these mu1 through mu k.
Mm-hmm.
So I'll say the cost of these. And then we're given a set of points x, and we're given a number k. So when we pick mu1 through mu k as our centroids, the cost of this will be something like the sum over all of the clusters or centroids I of the sum of the distances, distance here, the sum of the distances between the points in the cluster and that mean. So this will be the sum over x in, I'll call this ci, where ci refers to the set of points for which mu I is the closest centroid. So basically the ith cluster that is implied by these centroids.
Yeah. Okay, so that implies then that you have some initial mu I that you need to start with, right?
Yeah, for an iterative algorithm, that would mean we start out with some choice of mu's, and then we can update them and eventually find one that we think is a good representation of the data.
Okay, great. Yeah. And it seems like you have this other parameter here, k, which is like the number of clusters. How would you select a good value for k?
Yeah, so one common way is often referred to as the elbow method. This means that for every value of k within a certain range that we're considering, we perform some algorithm for that particular k. And then we judge how good that algorithm is according to this objective function or some other function on our clustering. And then we plot that. So for when k is larger, presumably our objective will fall because the points, there will be sort of fewer points in each cluster, and then their kind of average distance will be smaller. So as k increases, we'll see this curve go down. And the elbow method says basically when you're not seeing much marginal improvement in the objective, you should stop increasing k. So a good value of k is one for which the objective is good, but for which going higher than that doesn't help much.
Right. Okay. So that's kind of like picking the part of the curve that corresponds to like the bend in the elbow, right?
Yeah, sort of, yeah.
Yeah. Okay. Awesome. Thanks. Okay, so I'd love to see you actually implement this algorithm then.
All right. So see that there is a skeleton here. So I first want to think about some sort of design choices here. So we can take two perspectives is the way I think about coding up k-means. One perspective is to think about it from the point perspective. So for each point, we want to assign it to a cluster or to assign it to a centroid. And the other view we can take is sort of from the cluster's perspective. So we want to pick centroids, and for each centroid, maintain a list or a set of points that are close to it. Or for each cluster number, 1 through k, maintain a set of points that are in that cluster. So the way I want to think about this is in k-means, unfortunately, the centroids are always changing. And the set of points in each cluster are always changing. So what stays constant is the fact that we have k clusters and the fact that we have n, let's say n points. So since that's the case, I'm thinking that we'll sort of just maintain arrays, an array of length k, which says for the ith cluster, what is its centroid value currently, and then an array of length n that says for the jth point, what is the cluster to which we have currently assigned the jth point or vector.
Okay, the cluster index, right?
Yeah, the cluster index. It'll be a number from 1 to k or 0 to k minus 1.
Okay, gotcha.
Cool. So just to be clear, k-means refers to both this objective and a particular algorithm that heuristically tries to optimize that objective. So I'll be coding up the sort of the algorithm people usually refer to when they say k-means, also called Lloyd's algorithm. So so you've already given me this framework for how it works. So first we'll pick some centroids. Typically the centroids are picked either arbitrarily or randomly, like the first k points or k random points among our input points. So I'll do that first. So pick k random points from input to use as initial centroids. I will call this cluster to centroid. So just a bit of notation here. Throughout my code, I'm going to use I to refer to a cluster and J to refer to a point.
Okay, great.
Cool. So cluster to centroid will, I'm going to do this. So we have NumPy imported. So NumPy, we can randomly choose, I think it's rand int. Low should be 0, high should be n. N is the number of points we have. So this will give me a set of integers in the range 1 through n of size k.
Okay.
Yeah, so these I'll then use to index into the points, which will basically give me a choice of k random points. So those would be my initial centroids.
Mm-hmm.
Okay, so now we have this iterative algorithm, well, not converged. So in this case, I see this function is defined as having a maximum number of iterations. So basically, while we haven't spent that many iterations yet, we'll run this algorithm. So while I'll do this, while max iterations is positive, and then I'll decrement max iterations. All right, so k-means is sort of a two-stage algorithm. The first stage is we imagine the centroids are fixed, and then we want to record the closest centroid for each point. And I see that to find this helper function here, calculate centroid. So I'll use that. So okay, for each point j, I want to find I see. So calculate centroid is different. Calculate centroid is for the next stage. So I need to define, I want to define a new helper function myself called get closest cluster, maybe.
Okay.
This will take this will take an individual point and then an array of centroids, and then it will return the closest one among them. So I'll implement that later.
Okay. Yeah. So when you're getting the closest cluster, it's actually the same thing as getting the closest centroid, right?
Yeah, I think so. What the reason why I'm saying closest cluster is I'm going to return an index for a centroid or a cluster. Yeah,
Okay.
so I'm going to return a number I. This will just be easier to do bookkeeping for everything.
Yeah, that makes sense.
So I'll let I be this closest cluster of the jth point. And then pass this helper function our current list of centroids. So now we know which cluster number this point should be assigned to. And so now I need to decide what I'm going to return. So I think what we said was I want to return, well, my data structure, as I said, will be lists or arrays. So I'm going to have an array that says points to cluster, which is a length n array. It says for the jth point, which cluster I is it assigned to. So
Okay.
I'll just initially make this the all zero vector. So this will just mean that initially everything is assigned to the 0th cluster, because why not? I think that's okay for now. So now I want to update this. The jth point should be assigned to cluster I. I need another data structure for the next step. So the second step in Lloyd's algorithm is that once we have assigned every point to its nearest centroid, the centroids will have shifted. So the centroids from the previous iteration will no longer be the average of the points currently assigned to it. So we have to recalculate each centroid.
Okay, yeah.
And that means that I need to get the mean of every set of points in a cluster.
Mhm.
And I think that is where calculate centroid will come in handy. So I think for this one, NumPy should be able to do it. NumPy mean. So we can just take the mean of the points. And I think we want axis equals 0, so that will collapse the rows.
Right.
We'll return that.
Okay, great.
Okay, so we basically want to update this data structure, the array of centroids.
Mhm.
I'll do this for every I, or I in cluster, sorry, I in range K. Cluster to centroid at I. So the ith centroid should be calculate centroid at, for the points who are assigned, the points that are assigned to the ith centroid. So actually what I'm going to do here is I'm going to enumerate the cluster assignment. So now I'm iterating over the cluster numbers I and the points that are in the ith cluster.
Okay, gotcha.
Yeah, so now what this expression does is I'm saying for all the indices of points j that are assigned currently to cluster I, get those point values. So get the values of those vectors,
Mhm.
and then calculate their mean. So that will be the new ith centroid. And in the end, I want to return this assignment. So the mapping from points to cluster numbers.
Okay, awesome. And I think there was one more helper function that you hadn't implemented yet. Yeah, a couple of them. Get closest cluster and distance.
Right. So for this one, we could actually use any distance function, but typically what's used is the L2 distance, or the squared L2 distance.
Mhm.
And we can get that by using, okay, so we're given two vectors UV, which are presumably NumPy arrays. So we can use NumPy dot linear algebra dot norm. By default, this is a L2 norm of U minus V. And I think there was one more data structure that I did not implement. So remember here, I wanted to get all the points that were in the ith cluster.
Right. Mm-hmm.
So we have the inverse mapping. So we have the mapping from each point to its cluster, but we
Mhm.
also need a mapping from each cluster to the set of points that are currently in it.
Mhm.
So that's going to change every iteration. So I will make it here. So this will be a map from I to a list of points j assigned to a cluster I. And initially, that will just be an empty list for every cluster. And then this needs to be updated. So here, as soon as we've assigned the point j to a cluster I, we can add it to the ith list in this mapping.
Yeah. Mm-hmm. And for the line where you're defining cluster to points, I think you need the keyword in before range of k.
Sorry, where?
Where you're defining cluster to points. I think you're missing an in.
Oh, sorry. Thank you. Yeah.
Yep, there you go.
Great. So maybe we can run this and then just see.
I think you still need the get closest cluster implementation.
That's right. Okay. So for this one, we basically want to do a kind of argmin. So we want to iterate over the centroids and find the distance from the point to each of the centroids. So, and then we also want to return not only the distance, but the index I for that centroid. So I'll call this the closest cluster. I'll just make a none at first. And then we want to record the minimum distance we've seen so far. And this should be just some large number. So for centroid in centroids, and I'll again do this trick of enumerating the centroids so that I get its index as well. So if the distance between this given point and the current centroid is less than the minimum distance, we'll update this. And then we'll also update the closest cluster to be this one. Okay, and in the end, we'll return the minimum I.
Okay, perfect.
See if there's anything else I missed.
Yeah, seems like you're ready to try out your code.
Okay, so points was initially this 2 by 150 matrix, but now it's 150 by 2. Okay. Okay, and we're going to try to get these 3 clusters that you've generated. Okay, so we have this list of size 150. So we see that they're very grouped together. Hopefully that is a good thing.
Well, you can try visualizing it maybe to see what it looks like.
Sure. Let me minimize this. Okay. So to visualize this, I think the simplest way to do that is just to basically copy what you did and do a scatter plot. But in this case, the scatter function has an argument that we can use to basically assign different colors to different points. So we'll try to do that.
Okay, great.
Okay, so we'll just scatter, and we have, so this C is a color map. So we want to devise, it will help us specify which colors each point should have. Since it's 3 colors, I will just do this simple thing where we have RGB colors. Okay. I'll call this color map. And then the output of our k-means algorithm should go here. So what this is doing is I'm getting back from the algorithm this mapping from each j to a cluster number I,
Mhm.
and then I will be 0, 1, or 2. So in NumPy, this will give me, this will translate this from 0, 1, 2 to RGB.
Okay, perfect.
Yeah, so I need to rerun this cell so that the algorithm runs and gives me its output. Okay. All right, so here we found sort of a suboptimal clustering, but since there's a lot of randomness in the process, maybe we can run it again.
Sure, yeah, let's see what it turns out.
Okay, there we go. So that's a lot better. But that's good because we want to, it's more reassuring actually if we see that k-means doesn't do great every time.
Hmm.
Means that's sort of one thing that is true about it in general. So it's good to see that.
Right, especially since it's an iterative approximation that you have here, right? Okay, awesome. So can you tell me what the time and space complexity of this code would be?
Sure. So let's do time complexity. So it's just a bunch of loops. So a simple way to describe the running time would be the number of iterations, since that's a given. So let's say the number of iterations, I'll call it I, and then the number of points we said was n. The number of clusters is k. And what happens is we do I times, assign each point to its nearest centroid. So we do n times, get the closest cluster. So we have to iterate over all k to do that. And then the second step is we calculate the mean of every cluster. So that involves doing just a sum operation over all the points in a cluster. So that would be about k. That would be about one operation for every point. So for at most every point times every cluster. And then actually each of these vector operations, for example, taking the norm or the mean, will scale with the dimensionality of the data. So let's say that our points are d-dimensional. So each of these will cost, like taking the norm will take order d time.
Mhm.
So just multiplying all those things, because it's just a bunch of for loops, we get a running time of n times k times d times I. What's sort of unsatisfying about that runtime is that I is something that you might have to tweak in practice, well, as well as k, but I specifically, you sort of don't know when exactly will converge. But it turns out that is sort of necessary because the k-means algorithm is not an exact algorithm. So it's something that we usually provide as input.
Right. Okay, great. Okay, fantastic job. I think that's a good place for us to pause today. So let's debrief about this a little bit. What do you think went well for this interview, and what do you think you would want to improve on more?
Yeah, so this algorithm is tricky to code, I think.
It
I'm
definitely is.
very glad in retrospect that I sort of went with a simple choice of data structures, which is simply arrays.
Mhm.
That's pretty common in scientific computing, and maybe we can see why now, which is that if we had to maintain a set of points assigned to every cluster, that would change all the time. The centroids would change. The objects, the points would need to be hashable, which NumPy arrays are not, so they can't go in sets. It would just be a mess. So I'm really pleased with that choice. I realized I forgot to check some edge cases, like if k is less than 2 or if the number of points is smaller than the number of clusters. And then I also think that it would be nice to code up some additional convergence conditions. Like for example, in the past iteration, none of the cluster assignments changed, then we could already terminate. So that would be a way to avoid going up to max iterations as well.
Yeah,
So
perfect.
that would have been nice to code.
Okay, yeah, I agree with a lot of those points actually. And I actually thought you did a really fantastic job, and there's a lot to call out here that you did really well. So, for example, I really like that when we were discussing what the learning objective of k-means clustering was, you were able to explain both the intuition and the mathematical formula behind it, and that really showed that you know your stuff. As well as when you were going through your code, I really like that not only did you write really clear code, but you fleshed out the code outline first, so it was a little bit easier to follow that way before then filling out the helper functions. And you used a lot of more concise NumPy syntax too, which definitely made your code a lot more readable. So I agree with you that it would have also helped to maybe add in another convergence condition of maybe once the error has surpassed a certain threshold, or as you said, once the cluster assignments are no longer changing. Those are both great convergence conditions. As well as I think I would have liked to hear a little bit more of discussion when we were discussing what the learning objective is of how you can interpret the objective as not just minimizing the square deviations from the centroids, but also maximizing the distances between the clusters, or the distances between the centroids equivalently. Because it's always good to explain as much as possible the intuition behind these algorithms. Last of all, this isn't strictly required, but a lot of times with coding these types of algorithms, it also helps to discuss sort of like the runtime boundaries. So in this case, k-means is an NP hard problem. And I think it would have been interesting to go through the discussion of that a little bit more. But otherwise, this is really fantastic. Thanks for joining us today, Jimmy.
Thanks, Henry. Yeah, it was an interesting problem.
Yeah, for sure. Thanks everybody for watching, and good luck on your upcoming interviews. Bye, everyone.
Thanks so much for watching. Don't forget to hit the like and subscribe buttons below to let us know that this video was valuable for you. And of course, check out hundreds more videos just like this at tryexponent.com. Thanks for watching, and good luck on your upcoming interview.